Can I share my screen?
You can, or I have the slides up as well.
Yeah, why don't you do that, please? Thanks.
Can you see my PowerPoint presentation?
Yes.
Okay, so then I'll move forward to the agenda slide.
Okay, good afternoon, good morning, everybody, depending on where you are. Welcome to the September edition of Imaging Community Webinar. We are scheduling this out of this regular first Monday of the month cycle because of the Labor Day holiday. Nonetheless, we are very happy to have with us today's presenter, Dr. Satish Viswanath from Case Western University, who will present on computational imaging for precision medicine, a quest for generalizable AI models. If I could give a bit of background, Dr. Viswanath is currently assistant professor in the Department of Biomedical Engineering at Case Western Reserve University. The primary focus of his research has been developing new image analytics, radiomics, and machine learning schemes via radiology, pathology, and fusion of the two modalities and correlation towards more comprehensive biological quantitation of in vivo imaging data. He's applied his technologies to image-guided interventions, direct guidance, and quantitative evaluation of response to treatment, including radiotherapy, chemotherapy, and focal ablations in gastrointestinal cancers and digestive diseases. His research has been funded through the DoD, the Cleveland DDRCC, which he could tell us what that is, and the NIH. Without further ado, I welcome today's speaker. Thank you.
Thank you, Kevin. Can
you tell us what DDRC is?
Yeah, sure. It's the Digestive Diseases Research Core Center here at Cleveland.
Thank you.
Actually, you're going to be talking about some of that as well. I figured I might as well put it all in here. Okay, thank you very much for having me. As Kevan said, my talk is going to be about computational imaging for precision medicine, a quest for generalizable AI models. So we're going to talk about each of these things in turn, but to begin at the very top, where we are is the huge potential for AI in the world that we're in today. There's been acknowledgement from across multiple domains, from across the media to the number of different funding sources that have started to take notice of the fact that AI is an area that we need to focus on and really try and move up the ladder in terms of its impact. And the question really is, what are we doing with AI in this talk? So in this talk, I'm approaching AI from the perspective of computational imaging. So computational imaging itself begins, work back, it begins with the idea of precision medicine. So precision medicine is where we try to develop prognostic or predictive tools to try and tailor therapy for a patient based off a specific profile. So given a cohort of patients, if we have an effective marker, we might be able to figure out which patient should get which kind of therapy. So, along those lines, what we want to know is, okay, how well is a patient going to do on a particular therapy? Are we going to see progression? We also would like to understand the idea of predicting response. So can we figure out what's going to happen to the patient before therapy? Can we figure out what's going to happen to the patient after therapy? And all of these are going to govern that idea of precision medicine. And this sort of solution we are taking to this problem is to approach it from the context of computational imaging. And computational imaging itself is the idea of trying to apply computational techniques to enhance or improve standard of care, radiographic imaging data, in many cases. And radiographic imaging is commonly used in across a number of different diseases for non-invasively identifying where the disease is, and to some extent trying to understand what is the response, how do you evaluate treatment, and so on. And so what we're proposing is the idea of enhancing that with computation. So how do we do that? So I have a general workflow here for how computational imaging works. So you have a series of MRI or CT scans. We typically run some kind of texture analysis on that to compute texture features to characterize what is one of the heterogeneity in the image. So over here, the blue corresponds to things which are less heterogeneous, and red corresponds to things which are more heterogeneous. And then we can also look at different types of shape and morphological descriptors. So what is overall shape and specularity of these structures in the body based on the imaging. And then based off these measurements, based off these quantitative descriptors, we can then build a model where we can identify the most relevant features and then run that through a classifier and finally gain validation of that performance. And in this talk, I'm gonna be talking about some of the studies we've done in this context, but I'm also going to be talking about what do we need, how do we move forward? How do we move from the space of computational imaging and radiomics and start talking about them as generalizable AI? What does that even mean? And so I've sort of summarized that in sort of two challenges, and I'll talk about this as we go along. The first is, can we start to expand our feature set? Can we start to look at features which capture additional characteristics of physiology on imaging? So we have shape and texture. Can we start looking at new types of information? And then from the perspective of the model generation, how do we start to design these features in models so that they start to generalize better across sites and scanners, which has been a big focus of the work we've been doing over the last few years. So in short, to sort of summarize what I just said, we're going to be talking about computational imaging tools to enable better disease assessment. What do we treat? Where do we treat? We're going to be trying to characterize different types of response. What happened after we gave treatment to a particular patient, right? And this has been some of the work that has been showcased in recent news organizations and so on from our group. And then how do we start to make these tools more generalizable? And again, I will repeat these definitions further down, but I just wanted to throw these ideas out there to begin with, which is we can think of them in the context of being both repeatable and reproducible. And both of these terms are critical in order to understand that idea of generalizability. Okay. So that said, let's dive into how we can start to use computational imaging tools to enable this kind of disease assessment and response characterization. So a lot of the work that's ongoing in my group is in colorectal cancers. Specifically, we focus on rectal cancer, which affects about 40,000 patients in a year, 40,000 patients in the US. And this timeline here is just sort of a general clinical protocol for rectal cancer patients. They get diagnosed, we confirm there is disease, we stage them, they undergo some kind of therapy. After therapy, they undergo another staging in order to figure out how well the therapy worked. Then they almost all undergo surgery. And then they have a pathologic specimen to figure out, well, how well did we do with all of this extensive set of operations we've performed? And then after that, we start to follow up the patient depending on what this pathology reveals. But it turns out that almost close to 30% of the patients, when they look at this pathologic specimen after therapy, there's no tumor remaining on the specimen, right? Which means that the therapy was very, very effective. But that in turn begs the question, how do we start to what can we do differently with these patients? If they're benefiting so much from therapy, maybe they don't need to undergo surgery, right? If they don't have any tumor, we don't need to send them into surgery. And so the question is, how do we sort of revamp this pathway to make it more precise, make it more targeted? The catch is that right up front, as we start to look at the MRI and the biomarkers that require a diagnosis, these are not very predictive in their performance. So what we would like to do is somehow try to use the imaging here, since it's a computational imaging talk, to identify markers of response before treatment, so we can non-invasively start to personalize the treatment for these patients. So this is a study that we recently published in JMRI earlier this year, where we had about 100 patients, all of whom had rectal cancers, and it was conducted across 3 different sites here in Cleveland. And what we did is in all of these patients, we had the diagnostic scan, the scan acquired just before therapy. And we defined the pathology, the pathologic outcome for these patients as no tumor remaining after they've gone through their entire clinical protocol. So all the patients got diagnosed, chemoradiation, surgery, and then if they had no pathology, no tumor remaining on the pathology, they are considered to be a complete responder versus others would be an incomplete responder. And straight off the bat, we found that none of the clinical parameters were really associated with pathologic complete response. So starting out, we divided our cohort. We had a discovery site we had one set of discovery cohort where we looked at what signatures really start to look at this idea of differentiating responders and non-responders. And we found that one of the features that we've been developing in our group, which is called Collage, which is an idea of trying to look at the gradient organization within these tumors, collage revealed that there was a significantly more heterogeneity in patients who did not respond to therapy compared to patients who did respond to therapy. So that was very encouraging. That was on a diagnostic scan in the discovery set. As we moved on, and then we looked at our validation cohort of, which came from 2 independent sites, we found that that signature actually generalized really well to those 2 sites. When we looked at the performance characteristics, we're at about a AUC of close to 0.7, but that 0.7 is validated across multiple sites and scanners. The signature was resilient to 3 different sites, about 10 different scanners, and 2 different magnetic field strengths. And the signature was very consistent across all of these parameters. So, which means we're starting to move towards that idea of generalizability there with these kinds of features. So that's great. We now have a signature that we can find on the diagnostic scan, but you will notice that there is a follow-up scan that we can try to use as well. And so when we started looking at the follow-up scan, we realized very quickly that this is a very different beast from the diagnostic scan. So the catch here is that after chemoradiation, there are lots of treatment effects, such as fibrosis, that are present in these areas. So the problem is that visually speaking, for a radiologist, they don't know where the tumor is in these patients to begin with. So they have a relatively low accuracy in restaging the presence of residual disease in these patients after chemoradiation. So we set out to say, okay, what can we do to try and do something with this from the context of radiomics and computational imaging? And so, again, we had about 100 patients. This just got published last month in Cancers after being presented at RSNA over the past couple of years, where we had about 100 patients, close to 100 patients from across the 3 different sites here in Cleveland that we're working with. And over here, we used tumor downstaging. So in other words, is the pathologic stage of the tumor, is it low after chemoradiation on the pathologic specimen? We can define those as responders. And then we looked at, what we did is we annotated out the lumen and the rectal wall so that we don't need to worry about where the tumor is. We're just going for these structures, which are much more straightforward to identify. And we found that there was no real relationship between the intensity and the volume between these pathologic stages. So from the perspective of radiomics, we did 2 things. One is we looked at the morphology of sort of the shape and the structure of these different things on imaging. And then the other thing we looked at was a host of different texture features, including statistics, Harlick, Gabor, collage, and so on and so forth. So when we trained our classifier using one site, again, we validated on 2 different sites. One of the things we found was that higher pathologic stages tended to exhibit these more abrupt changes in the lumen and the rectal wall. And the hypothesis we have for that is that essentially if the tumor has regressed, so it's a lower pathologic stage tumor, it's a very regular structure. Versus if you have tumor sort of shooting out from the wall, it tends to get more distended and more irregular. And so the shape feature is essentially picking up this characteristic. So it makes sort of intuitive sense. The other thing we found was, again, going back to our gradient features, our gradient heterogeneity was much higher in patients who did not respond compared to patients who did respond. Once again, we trained it on one of the sites and we tested it and validated it on 2 other sites. And again, we have a performance of close to 0.7 consistently. Interestingly enough, combining the shape and texture did better than using either one individually. And then, of course, the model, again, we found we were able to develop it to be resilient enough to scanner and site differences. And again, we're talking about a number of different scanners and sites across in the study. So that said, before I sort of segue on to the next focus of my talk, I just wanted to give a call out. So some of the tools that I've been talking about over here, so I spoke about collage, which is our gradient heterogeneity feature. So through a recently funded UO1, we've actually started making these tools available to the community. So if you go to this website, radxtools.github.io or github.com/radxtools, you'll find our repositories for implementations of these tools. Over here, I'm showing you a video of the tool running in real time in 3D Slicer. They just loaded the image in, they're selecting parameters there and visualizing it for you. So it can be computed in 2D and 3D and essentially gives you a visualization and a quantitative measurement of the gradient heterogeneity inside the region of interest. So over here, since this is a generalized tool, over here we're showing it in the context of a lesion in the brain. So this is in collaboration with my co-PI, Dr. Pallavi Tiwari, also at Case Western. And then the other feature which we're going to be releasing, I think this week or very soon, is a feature to do with that with the idea of computing more advanced metrics of the surface. So looking at the surface topology and the irregularity. And again, this is again going to be released as a Python module integrated with a host of different platforms through this UO1. And I encourage you all to follow us at Radix Tools to get the latest updates on the tools we're developing in this context. All right, so we found some very interesting results with these sorts of tools. So now the question is, what can we do more? How can we start to design computational imaging tools to capture physiology and make them potentially improve their generalizability? So going back to the rectal cancer MRI image, when we look at the MR image over here, what I've done is I've just overlaid the MRI image with a heat map of the heterogeneity in the rectal wall. And then I've just sort of pulled out a few different regions from here. And what's interesting is we actually have a radiomic scene for this patient, but we also have, remember, the patients underwent mesorectal excision surgery. So we also have the pathologic specimen of patients. So the question is, how can we start to put these together? Can we somehow take the radiomic measurements and radiomic descriptors that we have and connect them back to the pathology and somehow use that to start to design the next level of features? Could we, essentially we have heterogeneity. Can we start to go beyond heterogeneity? So the first part to that is to try and figure out how do we start to map things from pathology onto imaging and figure out how to design our features better. So this was a study that came out in academic radiology a year or so ago, where we had a set of these patients. We had pathologic specimens together with MRIs. We had our clinical experts help us identify landmarks on the MRI and the pathology, which we then used to map these. And then that allowed us to get a very detailed mapping of the pathology onto the MRI, which we then validated with an additional set of landmarks. And we found a relatively low target registration error. And this is also a tool we'll actually be releasing through that UO1 that I mentioned a minute ago. But what was interesting is if we start to plot how these, how these different pathologic annotations function as a marker of response. So, we have our pathologic annotation here. We've registered it to the MRI. So different colors here correspond to different regions, pathologically mapped regions on the imaging. And this is all on a post-treatment specimen. So the first color over here, the blue region over here is fat. So now the y-axis in this plot is the patient, and the x-axis is just intensities. And these are basically the sort of distributions of these intensities in these regions, just sort of plotted, side by side. So what's interesting is that right at the complete response region, we have very distinctive pathologies occurring, even on the imaging scale, right? We have very distinctive signatures between fat and the other end is fibrosis, compared to poor response, where everything gets very muddled up. And then you have this, the tumor is in there as well, and it's sort of intermingling in there. So there seems to be, A, it's obviously very hard to visually tell these conditions apart, but B, there seems to be sort of a spatial interplay in terms of how distinctive, how separated, how many distinct compartments we have on the imaging when we start to compare it to the pathology. So in order to understand this a little bit better, we designed a new descriptor. And so what this descriptor, the way the descriptor works is we go in, we have our radiomic scene. And so then that's the heat map we have over here, where blue is low heterogeneity and red is high heterogeneity. And then we take that scene, and remembering that the pathology has a series of different compartments, we convert the radiomic scene into a set of different compartments based on the radiomic values themselves. So now we have, essentially, you can see that there are different tissue types in here, all of which are interacting. We have different compartments, all of which are also interacting. So we can then build a graph on top of this in order to compute our descriptor. So a descriptor form is made of two parts. The first is a spatial descriptor, which sort of describes how these compartments interplay with each other, how adjacent they are, how many of them are adjacent to how many other ones, and then the textual descriptor. And so one point I'll note here is that for the sake of simplicity, I've sort of partitioned it into three compartments. We have low, medium, and high. We could obviously tweak this as we need to. So, when we started to look at this in more detail, so over here, what I have is we started to study this in the context of rectal cancers. So again, we have our MR images, we have our annotation. And now in this case, we're looking at outcomes after therapy again. So these are all post-treatment scans. So in our discovery set, what we found is when we run our heterogeneity map, we see a difference. Visually, it looks different. There's more red and yellow and then more blue and red here. But if we look at the statistics, of the thing, which is what we would typically use in radiomic analysis, the statistics are not very separable, right? So that's a problem. So visually we see something, but statistically we don't, which is likely because we are seeing the interactions and statistics are not capturing those interactions. So on the other hand, if we use radistat or our radiomic spatial descriptor, what we're able to do is we're able to develop the signature for the textual component as well as the spatial component. What you'll notice is the textual component has a lot more interactions of one type compared to the spatial component, which has many more distinctive interactions, which goes back to what we were seeing in the pathology as well. So again, we did our training on one side of about 44 patients, and we validated it on our second side of about 30 patients. And again, we found that the signature actually generalizes relatively well. The same, very similar, very same signature is observed both in training and validation, the same distinct compartments, the same kind of spatial organization. Quantitatively, from an AUC perspective, this sort of bumps us up further, going from that 0.7, it's taking us up to close to a 0.8 now. So the addition of new piece of information is not only giving us sort of more intuitive descriptors, but it's also potentially increasing our performance. So as we, the radistat method itself works based on a series of parameters. So we conducted a sort of a parameter sensitivity analysis, and it was sort of gratifying to see that the signature was very consistent across all the different parameters that we examined. Then the question is, what do these signatures, what are these compartments, how do we know for sure that they are really picking up what we want them, what we say they're picking up? So we go back to our pathologic specimens. So we mapped our pathologic specimens onto imaging, then we computed the radistat maps for those specimens. And we tried to identify which expression maps, which of these expression levels correspond to which of the pathologic compartments. And what we found was that if you actually looked at it, the fibrosis tended to be falling more within that low expression region on this map, right? Versus the cancer tended to fall more in the high expression region of this map. And so that suggests that there is these compartments are somehow being driven by those, different tissue types that we started with. So it sort of came nicely full circle. And we also found that maybe an association between these signatures and the continuum of pathologic tumor regression grade in these patients as well. So we've spoken about sort of taking texture and enhancing it to the next level using sort of spatial ideas. So then we turned our attention to shape. So in the context of shape, if you remember what I had said was that in patients who regress, we tend to have much more regular structures, both in the lumen and the rectal wall. Compared to patients who did not regress, we tend to have more irregular structures. So if we sort of think about what that means is in the context of patient who regressed, we essentially have a difference in terms of how that structure has deformed, right? So in the case of a patient who has regressed, we have much more sort of uniform deformations occurring, versus in a patient who did not regress, we seem to have much more non-uniform, irregular deformations occurring. Similarly, we can sort of make the same sort of leap, if you will, for the rectal wall. Similarly, the rectal wall appears to be more regular in one case and more irregular in the other case. So if we're trying to compute this idea of regularity, irregularity, and trying to enhance beyond just simple shape descriptors, it seems that we're talking about, almost like expansions and contractions. So the idea is we need to compute, so which suggests that we need to start looking at deformations. So deformations might be sort of the next level of shape descriptors. But the catch is, in order to compute a deformation, you need a healthy sort of baseline to begin with. So you need an atlas to begin with. And that atlas ideally should not have any disease in it, because otherwise you won't be able to figure out what the reference with, how the tumor scene has changed with respect to the healthy atlas. So we went in and we built the first rectal atlas from healthy patients. So we used sort of healthy rectums from patients, in this case, who had prostate cancer, but we've sort of done the same thing in the context of other cancer, of other gynecological cancers as well. So we've taken these annotations and built a healthy rectal atlas. So these are patients who have no tumor in the rectum at all. And then we take a patient who does have tumor in the rectum and we co-register these onto the healthy rectal atlas. And we can then start to look at whether we have expansions, contractions. And so that's what these arrows correspond to over here. They correspond to whether we have expansions or contractions. And then we can look at this and compute the magnitude of these contractions or expansions, and that'll give us a deformation magnitude inside the rectum. We can similarly compute a deformation magnitude just outside the rectum. The idea being that some relationship happening there in terms of how those structures are deforming, expanding, and contracting both inside and outside. If you can compute that, it might prove to be a very useful marker. So this is work that we presented at MICAI last year, where we found that the deformation statistics within that rectal wall are distinctly different. A lot more deformations occurring in patients who are non-responders compared to patients who are responders, which sort of goes back to what we started with. The hypothesis was that the deformations were different, they were more irregular, and that's reflected in the more irregular deformations that we see over here. So looking into the studies, we have our maps with the arrows showing the contractions and expansions, and then we have the deformation magnitudes where we have the red corresponds to regions which have high deformations, and then we found using these deformation features actually takes us all the way up beyond 0.8, takes us closer to 0.85 in terms of differentiating between good and bad responders. And now this again we validated across sites, so this feature also seems to be resilient to site-specific differences to some degree. So before I sort of go into the next part of my talk, which is on the idea of generalizability and what we need to think about in that context, I just wanted to make a quick segue to Crohn's disease. So this is some work where it sort of brings together some of the other features and methods I've been talking about. So I just wanted to quickly touch upon some of the recent findings that we've had here, where we found that we can use radiomics to try and assist in this idea of trying to find biomarkers to predict outcomes in Crohn's disease. So it's a big problem. Over 700,000 patients suffer from it. It's not cancer, it's a disease. But the catch is that even though we have high resolution MRI, they don't quite have good markers to figure out what's going on with every patient. And so we did a study, when we started the study a couple of years ago, we did a study where we had a set of patients where we had bowel MRI scans. So in these patients, since this is not cancer, the question is, how do you define response? How do you define somebody who is going to respond to therapy versus somebody who is not? We said, okay, if patient has Crohn's and for a year after they were diagnosed with Crohn's and they're given a therapy, if they were stable, we consider them to be a responder. If they within a year, if they get surgery, they are considered to be unstable. They do not benefit from the therapy, so they are a non-responder. And then if you were stable for longer, that's a responder. And so we got the terminal ileum here. That's the region of interest that we've annotated. And we did radiomics on that, just standard radiomics to begin with. And what we found was that we found very distinctive differences between the patients who did respond and did not respond. Again, you can see non-responders tend to have more heterogeneity. So again, it's interesting that the signature seems to generalize across different diseases, across different sites. And the performance for this in sort of limited cohort of about 45 patients is close to 0.77 in cross-validation. But Crohn's disease actually has multiple hallmarks. So one of the hallmarks of Crohn's disease, so here we have an MRE scan. So this right here is where the disease is. It's sort of the bowel wall gets thicker. But then you have all of these other regions in the body that are of interest as well. So there's mesenteric fat, or the visceral mesenteric fat that appears over here. And then you have the subcutaneous fat that appears on the outside. And what they found in Crohn's disease is that these different fat regions also have a relationship to the inflammation, right? So going back to our idea of trying to design new features and trying to interrogate new regions with radiomics, we started to ask the question, could we somehow start to interrogate these relationships a little bit better? So in this study, so what we did is we went in and we built an automated tool. So these are 3 different patients. So the top patient is a patient who had no disease. They're actually a healthy control. And then these 2 patients both had Crohn's disease, but one of them was stable on therapy and the other one did not respond to therapy. And so in all of these patients, we annotated out, we automatically segmented out the region of the mesenteric fat inside the body. And then we started to look at radiomics of this. But as a sort of sanity check, we said, okay, first let's look at radiomics on the outside. So technically the subcutaneous fat is just fat. It's not very informative. We found that there was no real signature from the radiomics in that context. But if we instead look at the mesenteric fat and we start to actually interrogate that with radiomics, we see that the activity in that region keeps increasing as a function of the disease. So the most, if a patient is a non-responder, they tend to have a lot more activity compared to a responder who has more activity compared to a healthy patient. So it's interesting that there's a signature there that we can interrogate with radiomics. And validating this across 2 different sites, we achieved an AUC of about 0.82 on about 70 patients from across 2 different sites. And this is some work that we're just putting out for under review. So that brings me to sort of the next phase of the talk, which is we've spoken a lot about different computational imaging tools. We've spoken a lot about How do we start to design them and interrogate other regions with them? But how do we start to make them generalizable? What do we mean by this idea of generalizability? So generalizability itself, essentially comes from the concept that, all machine and deep learning models are going to be impacted by imaging artifacts and changes in imaging conditions. So here I've just shown brain data from the TCIA, and so we have a lot of MRI scans which are of great quality, but then we also have MRI scans, which is to be expected since it's a clinically acquired cohort, where we have a series of different artifacts. We can have artifacts of aliasing, noise, and shading. Problem is that these artifacts are going to dramatically distort anything that we're going to try and do with these images, right? So maybe that we pick up the artifact and then we're not sure if that's an artifact or it's some kind of subtle cancer recurrence. The other problem is, if we start to look at the voxel resolutions of these patients across different sites, we tend to see a huge variance in voxel resolution across sites. So then the question is, how do I try to figure out if my method is going to generalize to new sites, if I'm going to have fundamental differences in such a thing as voxel resolution when we go from site 1 to site 2? So to address these and other questions, we've developed a new tool called Marquee, or MRQY, Marquee. So Marquee is essentially a quality control tool for MRI datasets. It allows you to check the quality of large cohorts, visualize the trends in quality, and is intended to be a very quick, robust way of evaluating what's going on in a cohort before you start getting into analysis. So given large dataset, you can run Marquee on the dataset. It's pretty quick. We've optimized it to be about 40 seconds per dataset. There's no real specialized hardware. It runs about 40 seconds on my laptop right here. It's open source. It's available online. I'll put the link up in a minute. But the idea is you take a data set, you run Marquee on it, you check what's wrong with it, fix it. So you process it in some way, run Marquee on it, and then you sort of iterate on this process till you're happy with the data set, and then you move on to the radiomics. So it's sort of intended as a pre-analytical step. So a very quick video to show you how Marquee works. So over here, we're just loading in the Marquee file, which is it's a locally hosted text file, HTML file, which then loads in the results of running Marquee itself. So the front-end interface. So this is the front-end interface. It runs in a regular web browser. So there are different sections. There are tables of the different measurements that we extract. We extract a series of metadata. We extract a series of measurements related to noise and variance and signal to noise ratio and so on. And then we visualize these measurements using these very interesting visualizations below. So this is this one is called a parallel coordinate plot. So the idea is to show you where do you see a lot of variance, where do you see a lot of agreement. And then below that, you have scatter plots to show you the visualizations of how the data sets arrange themselves in space based on these measurements. So you can very quickly look at any given data set. It'll highlight it across the entire interface. So here you're clicking on a data set, it highlights it over here. You can also visualize the trends in terms of a bar plot. So the bar plot just shows you if there are obvious outliers. There'll obviously be either very low buildings or very tall buildings in the plot. And then you can do this for different measures. And as you go through, it'll visualize the images. So if you find an outlier, you can very quickly see what's going on with that particular data set. And then it's a completely interactive interface. You can click on any of the points in these things to show you. So this shows you the different clusters that appear in this data set just based off the raw data. And then that allows you to sort of go back and forth and sort of say, oh, I see a problem here. Let's go up here and so on. So Marquee is available online. It's available through GitHub right now. You can go and get it. Please feel free to. It's in active development. We have a wiki and tutorials on how to use it. It is a sister project of an effort going on at Case through Dr. Andrew Janowick, who you may have heard of, has created a tool called HistoQC. Marquee is a sister tool to that, again intended now here for quality control of imaging data sets instead. So we've actually generated some very interesting results with Marquee on TCIA cohorts themselves, and these results are available right now on the TCIA. So these measurements are already available on the TCIA for people to look at. So we've actually done it on 3 different cohorts, and we found artifacts and batch effects. Batch effects are essentially site-specific variations in these TCIA cohorts. So this is just a visualization of the Marquee interface. So if we just zoom into this particular plot right here, so this is for about 133 TCGA GBM brain datasets. These are all T1 post scans with about 7 sites in them. If we zoomed in, so we found that, I'm just showing you a quick exemplar of how you can use Markey to find artifacts. So in this case, we found that on this particular measure, which is the CJV measure, we found that we had a very clear outlier. When we visualized the outlier, we found that there was a very clear contrast difference between the outlier and the rest of the cohort. Going on to the rest of the measurements, if you combine all the measurements and you make a scatter plot of all of them, you actually find 7 distinct clusters in this cohort just on the raw data itself. So that means you can identify any one cohort with over 90% accuracy if you were to use this data without doing too much to it. Of course, we have our processing pipeline, so we ran that on this, which included different steps of bias correction, standardization, some amount of resampling. And with that done, we were able to fix some of these issues related to the outliers, as well as and make this whole space more homogenized. So in theory, now the radiomics should be a lot more resilient to the site-specific differences that you do have on the original data set. We've done this for multiple data sets. We've done it for another GBM data set, as well as the TCGA-CESC is actually an endometrial cancer data set. It is also available. Going back to our rectal cancer cohort that I mentioned earlier, we ran it on that as well, just to sort of see if Markey will generalize, no matter what body region you're acquiring the MRI for. And so over here, we have about 100 different MRIs from 3 different sites. And again, you can see we are able to identify very clear differences. We found an outlier right here. This patient had more noise than the rest of the patients. And now again, if we look at the 3 sites over here, this is now rectal cancer, mind you, we're still able to find those site-specific variations, indicating we need to do some amount of processing on this data set before we do all the radiomics and so on and so forth. So we're able to fix the imaging data before we start running radiomics on it, but is that enough? Does that suffice to ensure that we have some kind of generalizable model? So the catch here is that we have differences in scanners, magnetic field strengths, we have differences in the voxel resolutions, we have differences in imaging parameters, and all of these are going to contribute to the radiomics being different, even though we might have processed the data many different ways, and Markey reveals that it's already homogenized. It may still be that there are differences in them, and we actually see this. When we look at the radiomic signatures for these 2 patients coming from these 2 sites, we actually found that the signature is quite significantly different. There's almost no relationship between site 1 and site 2. So the question then is, how reproducible are radiomic features? How reproducible can we evaluate them as being? So in a study that we published that we presented at RSNA and DDW, the first place we looked at this in the context of Crohn's. So over here, what we have is we're now looking at CT imaging. So we're now trying to figure out how consistent are radiomic features across different CT parameters. So here we actually have Crohn's patients who have disease and do not have disease. And then we have a few different variations of dose. So we have 100% dose, we have a reduced dose, and then we have different types of reconstructions as well. So the question is, can we identify radiomic features which are resilient to these variations? And so a cohort about 100 patients, what we found was that in general, again, disease patients tended to be more heterogeneous. And what was interesting was the signature actually did generalize across these different variations. This was, I think, one of those collage features. And then if we looked at the performance, training on even just the full dose gave us a very consistent performance across all the different doses and variations with no real significant differences in the classifier performance. We've also conducted a similar study where we've looked at variations in imaging parameters, MR imaging parameters now, in a multi-site setting, which we published in Journal of Medical Imaging a couple of years ago. So what we did here is we looked at 4 different sites. We have 147 MRIs. And then we looked at the reproducibility or the stability of a radiomic feature across the different sites. So in this plot, this is a feature that has good stability or has low instability or is highly reproducible, has very consistent values across the sites, whereas a feature that is not very good has inconsistent values across the sites. What's interesting is that if you look at the radiomic descriptors themselves, we found that in general, Haralek features, the co-occurrence features, tended to be very, very stable across all the different sites, versus something like a Laws feature tended to be very unstable across the different sites. So that's interesting, but by itself, that just tells you that different radiomic features have different characteristics. If you compare that to the AUC of the features, in other words, we're now looking at a trade-off between the reproducibility and the discriminability, or how well a feature is able to discriminate between tumor and non-tumor in this case. what we found is that we actually have very distinctive clusters that tend to appear. So the laws features, you have a few laws features which are very stable, but not very discriminable, and then a few laws features which are very unstable and not very discriminable either. So these are really poor features. Comparatively, we have hierarchic features up here, which have a nice trade-off. They're relatively stable and discriminable. The Gabor features tend to show a little bit of variance in terms of how stable they are. So this revealed to us that there were some very important trends in the radiomic features that we needed to account for if we want to actually use these radiomic features more consistently. So applying that concept to rectal cancers, we decided to run the study where we took healthy rectal MRIs in order to compute how stable the features are based on a healthy ROI. And then we have our patients who actually have tumor, and we can compare these to identify which features are stable, and we want to keep those. The features which are unstable, we'd like to get rid of those. So potentially, we'd like to improve our performance by doing that. So again, a plot of what the performance of the different features are with respect to the reproducibility. We set a cutoff, and we keep the features that we care about. And when we look at these features in more detail, we found that the features that we kept that were highly stable and highly discriminable tended to have very consistent signatures between a discovery and validation sites, right? So we have on the left here, we have a responder. On the right here, we have non-responder. You can see that the signature generalizes very nicely between is quite different between the responder and the non-responder, but it's very consistent between the discovery and the validation cohort. And this is actually, I think it's a collage or a hierarchic feature. By comparison, if we were to look at the laws feature, we actually see that the trends almost completely invert themselves when we go from training to validation. So that's a problem. This is the kind of feature that would have been included if we were not applying some kind of reproducibility criterion in order to prune our feature set. Using those features to run our classifier, we find that regardless of the feature selection scheme, using a stability-informed feature selection approach tends to significantly improve our performance. It actually generalizes even better in validation. So with that, I sort of draw my talk to a close. So we spoke about computational imaging tools, how they can enable new types of disease assessment and treatment evaluation and enhance the use of imaging. We've presented some of the new radiomic features that might be able to better capture known disease phenotypes, such as organization and deformation. And then those kinds of features are the ones that tend to be more generalizable. So in order to ensure that, we need to control for sources of variation. We need to identify how reproducible or stable features are. I have the links to some of the tools that we put out there. So we have Marquee, which is our quality control tool over here. And then we have the tools that I mentioned coming out of our UO1 or new computational imaging features available also on GitHub. And then you can always follow me on Twitter for more. And before I conclude, I just want to give a shout out. We have some very exciting events coming up out of CASE. So we have our Artificial Intelligence in Oncology Symposium happening on October 19th. You can register. The registration is still open. I think early bird registration is still open. And then Dr. Tiwari and I are actually co-organizing a tutorial at MICAI 2020 talking about some of the challenges in treatment response assessment in oncology as it relates to our UO1 that I just mentioned. And registrations are open for that as well. We have in both symposiums, we have an excellent lineup of speakers. We have invited speakers from across radiology, pathology, oncology, drug discovery, who are going to be talking about different aspects of artificial intelligence in oncology and treatment response and so on and so forth. Of course, I'd like to acknowledge the funding agencies that make all of this possible. And of course, the excellent team that I work with who do amazing work every day, no matter where they are. And then I get to sit here and tell you all about it. So thank you very much for your attention. I can take any questions you have.
Thank you, Satish. That was a great presentation. Any questions?
Yeah, this is Vikram. So with regard to the rectal cancer work, you showed some area under the curve, graphs. And I presume these are all based upon the post-treatment pre-surgical scans, correct?
We've done it in both. We've done it on both the pre-treatment as well as post-treatment.
Okay. My point is that with the pre-surgical scans, the decision point is, should the patient have surgery or not? And if the patient has a very high probability of having a pathological complete response, you might skip the surgery. But I think the bar for that is going to be very high. And I don't know if you have what your clinicians have said about how high that bar needs to be. On the other hand, for the pre-treatment scans, if you can identify the patients who have a high likelihood of not having a pathological complete response, then you can intensify the treatment. And I think the bar for that might be actually lower. So I was just curious whether, what is the feedback from the clinicians about where the bar is for the pre-treatment scans versus the pre-surgical scans, because I suspect for the latter, the bar would be much, much higher, probably close to 1.0 AUC.
Yeah, no, you nailed it almost correctly. Exactly, the bar is going to be a little bit lower for the pre-treatment setting than the post-treatment setting. That said, the post-treatment setting, they won't even, they're already currently, there are ongoing clinical trials, and they're already, in many cases, they're starting to move to this paradigm of doing the watch and wait and the monitoring. So this would essentially be a triage mechanism to put them on, give them more confidence in putting that patient into watch and wait. So yes, the bar has to be high in that we have to be very confident about how, that there is no tumor remaining, but it may not need to be super, super high either, because they are going to be doing very intensive follow-up for any patient that they don't send into surgery. So it's also a question of, how that interplays with the clinical, how our, the predictors we are building interplay with the clinical protocol. So the idea is if we're able to improve that, then of course we would be able to do much better. In the pre-treatment setting, again, you're right. The idea is to try and intensify treatment for the non-responders. The catch, it's actually a little bit trickier on the pre-treatment setting, because the idea of sort of, what do we do with that patient is a little bit more of an open question, right? They could intensify treatment, but if the patient is just not going to respond to chemo radiation, then is there something else I can do? And that's where it starts getting a little trickier. So the feedback I got on that
but
front
I think that's very helpful for selecting patients for clinical trials.
Yes, absolutely.
That would be,
that's what I was about to say. Is they said, well, we have clinical trials, and we're trying these. In some cases they're trying immunotherapies, they're trying, more targeted therapies. Maybe they want to try intraoperative surgery, radiosurgery. So they said, we could start to look at those kinds of therapies if we knew these patients are going to benefit more from that rather than the standard of care chemoradiation.
So to make a long story short, what is the area under the curve for the pre-treatment scans?
So the area under the curve for my predictor, or what they want?
No, in terms of predicting pathological complete response,
right.
Is it better than flipping a coin?
Yeah,
at this
for
point?
sure. Right now we are currently at somewhere between 0.7 and 0.75 AUC. Granted, that's not earth shattering right now, but it is validated across multiple sites. So it's more confident to me than it would be otherwise. Right now, they don't have. Right now, the existing risk stratification markers they have are not are not predictive. They can use them for assessment to some degree, but they're not predictive yet. So we appear to be inching more towards the prediction side of things on that front.
Okay, I'll talk to you more offline about it.
Sure, absolutely.
Other questions for the speaker?
When you're normalizing the images across centers, I don't think you talked about in detail what you do. Are you saying that's the preferred practice before doing radiomics, is to do the correction? And if so, what is the methodology? Because there's many ways one could do that.
Yeah, that's a great question. So I'm suggesting that when we start dealing with multi-site cohorts, multi-scanner cohorts, we need to be careful about the way we start to normalize and correct them. And potentially we need to start applying these kinds of quality control mechanisms to really confirm that there are, the issues that we found to begin with are actually being removed. Because we've actually found cases where if you, for example, in the rectal cancer cohort, we started out with, okay, the standard pipeline is we've got to do some amount of resampling. We may have to correct the bias field. We may have to do some kind of standardization. And we found that the marquee plots that I was showing you, they started to get worse and worse in terms of the differences between sites, because some of those operations are not needed. So, well, as opposed to laboriously sitting and going through 100 scans, it gave us a very quick way of saying, okay, no, we need to correct these aspects of the scans. Maybe we need to do some additional processing of the scan in order to correct the area of interest for us, and then run the downstream analysis. So in terms of the specific pipeline, I can tell you the pipelines we've used over here, but I think the more critical piece, the message I have is, when we're running those pipelines, we need to be having some kind of almost like quality control to confirm that the pipeline is working and doing what we want it to do.
I have a related question. How do you decide whether what is indicated by marquee is not a false positive effect?
So that's where the interface comes into play. So I'm trying to let me in this interface. So the bar plot that we have over here, essentially, if you think about what you're trying to do with the idea of processing these data sets, what you're trying to do is you're trying to make them more consistent, right? So that's why I was saying that the way you would use it is you would run marquee, run a set of processing steps, and then rerun it and see if your metrics have overall improved or become more consistent. And that was something we had seen in this study where we had, a significant deviation here. After we ran the analysis, we found that we were able to sort of make the data set much more consistent. And that's what's important from the radiomics perspective, because if it's not consistent, the radiomics are going to pick up the differences just due to those, just due to small variations.
Okay, thank you. Any other questions for?
Yes, this is George Redman. Do you see this effort going beyond deep learning to support cancer imaging research?
Yeah. Hi, George. Yeah, absolutely. I think the idea of doing these kinds of generalizable models, these kind of generalizable tools that can pick up better signatures, I think that's crucial for. In this case, I've shown it primarily in the context of radiomics, but if you would imagine deep learning, if you would imagine even clinical imaging programs, I think the same sort of ideas resonate there, because over there too, you need to ensure that the data sets are of consistent quality, that the artifacts are not going to throw off the models or the radiology reads, etc. So I think it becomes a really key part of any of these pipelines, is to make sure that these things are working the way we would like them to before we start running all our analysis on them. Somebody had raised their hand. I don't know who that was.
This is Seferino from RRP. May I ask a question?
Sure.
So you mentioned the difficulties with radiomics features being robust, so that you run it again and you may have completely different answer. I think because of all these uncertainties, of course, you do have case studies where with 100 patient cohort, you were able to demonstrate certain features that seem to be robust enough. But it's still, I mean, it could be flaky, and it could be just heuristics. The question is, I think the word predictive is too strong for what the actual results demonstrate. And it should only be correlation. And have you ever done any like Bayesian kind of measure or metric for which you can you can show stronger than correlation between those features and how the tumors responded?
So you're asking, have we done a Bayesian modeling to figure out how predictive the features truly are? Is that?
Or any metric that you can have.
So I'm actually so in this context, we've not done the Bayesian modeling. We've done it in the context of other cancers and diseases and found some interesting trends. Your point about the about calling it predictive, I agree that that does, we're not quite at predictive yet, because to truly confirm prediction, you would need to run it sort of prospectively or on a clinical trial data set of some kind where you show that it really did, differentiate your treatment groups or your response groups, in a truly blinded fashion, so to speak. Right over here, we're training it and then we're validating it. So yeah, so your point is well taken about calling it probably more associations or more, correlations, if you will, in terms of treatment response versus the radiomics. But the other point you mentioned about the robustness and whether it's sort of how sensitive it is and so on. So there are some efforts that we are undertaking right now where we're trying to understand exactly what the performance bounds are. Because if you think about it, all markers have a certain amount of variance present in them, correct? So it's not as though the existing clinical markers are always exactly where they need to be. These are all biological measures. There's going to be some amount of variance in them. I think the point with radiomics is we need to move it to a place where we have those bounds better defined for us, where we can say, well, if this is your range, if this is the sort of input that you're giving to it, this is the range of values you're going to see, and this range is as tight or as broad as you want to consider for a particular problem. It's okay. So based on this, I'm now confident of making this a marker for actual clinical use. So I think it's a little bit of both. I suspect we're going to start to see efforts where we start to move radiomics in that direction in terms of really validating it in those settings, as well as understanding the performance bounds on radiomics. Like how robust, how repeatable is it? And we're seeing a lot of those studies coming out nowadays, and those are all towards that same idea: is how robust, repeatable, sensitive is radiomics to the input data? Like if I is it, we've all seen the studies in deep learning where they have this really robust deep learning network supposedly, and they give it an image with a little bit of noise and it goes completely bonkers, right? So the difference here is that potentially with radiomics, we might have a way these efforts are going on in deep learning as well, where they're trying to figure out ways to make the networks more robust. And I'm saying those kinds of efforts have to be undertaken in radiomics as well, where we figure out what are the bounds, we make them more robust within those bounds. I think then we get to that truly predictive assays that we're all looking for.
Quick question,
Sure.
if I may. Yeah, this is Fred Pryor. So I was really interested in your approach to identifying issues with the data quality and trying to improve those. And I absolutely agree with you. This is an essential problem that we all face when we try to use particularly large collections of public data. But you were working on, my specific point has to do with cleaning up neuroimaging data. So I was interested in your approach for doing that. I would have used FSL's fix to solve the same problem, which characterizes the image quality issues in a different space, in an ICA space. So what's your thought on how do we come to some standard or some agreed upon, this is the best way of solving this problem?
That's a good question. I think the catch is we all have our own pet pipelines and our own pet tools in some sense. So you spoke about FSL fix. There are, in the neuroimaging space, there are tools. There are so many different tools. There's MRI QC, which is a tool that works not similar to ours, but along similar lines. There is there's another free surfer based tool that I know about. There's Lab QA. So there are a few of these tools that exist out there to try and do these kinds of quality assessments. I think the place we're sort of getting lost on is a lot of the tools end up going towards the idea of just trying to find good quality. And I think, just sort of say, okay, I have 1,000 data sets, I have 100 data sets, which 80 data sets in them are usable and which 20 are not usable. And I think the fact of the matter is, for some of these problems, we can't really afford to throw out a data set without being sure that we can't somehow make its quality more consistent with the rest. So I think quality itself, we have to basically come up with a way to, say, okay, I have a cohort. I've now defined the performance, the sort of the quality bounds of my cohort, if you will. Like this is the level of noise and homogeneity and so on that I have in this cohort. And now I'm running my predictor. And how did I do? Oh, it didn't do so well, or it did well for these reasons. Okay, great. Now, if I get a new cohort, can I somehow match these performances so that I can now, the tool is also more generalizable because I tested the tool in a particular setting. Can I now confirm the tool continues to work as long as I keep bringing it back to the setting? So I think the answer to your question is, I think where we have to focus is more on the idea of, rather than focusing on, just purely the processing or just purely the specific tool we're using for quality assurance. I think the key is to try and figure out what are the bounds on our quality that we are working with, right? How do we make sure that our tools, that our images and features are working with a particular level of quality so that we can ensure that all of our things are working better, right, more consistently overall. And speaking about the specific tool you mentioned, that was one of the reasons we developed Marquee the way we did, is because I was trying to run some of those tools on the rectal cancer data set, and I found there was nothing. They were all very, very specific to brain because they all use the brain atlas and so on. So we had to go in and sort of recreate those a little bit for our application. So hopefully that answered your question.
Yes, thank you.
Okay, thanks. We're at the top of the hour, and if there are no further questions, I'd like to thank our speaker, Dr. Viswanath. Thank you. That was an excellent presentation.
Thank you so much for having me.
Yes, we'll continue this session with update on TCIA. I think John is going to give that update.
Yes, I'll take a few minutes to update latest developments from TCIA. Let me share my screen. Try that again. Here we go. Yeah, thanks so much, Dr. Viswanath, for that really interesting talk. And I just wanted to start by showing everyone on the call the actual page on TCIA with your Meraki quality measures for these 3 TCI MRI data sets. The two of them from TCGA, GBM, and cervical, and then a GBM data set from CPTAC. So you can access the actual output of the Meraki tool from this page and see if that, the exposed batch effects or what have you from the Meraki tool have impacted any analysis that might have been done on these data sets. So we thank you for contributing that data. In